Hi, so for today we're going to talk about electrostatics, electric charges, and forces. So in this video, we're going to talk about the basic of electrostatics, what are the different types of charging, and the basics of what we call the charges, what are these charges, and basically the Coulomb's law, okay? Wherein it states that there is an electrical force or mechanical force existing between two charges. So let us first start with electrostatics. What is electrostatics? And again, electrostatics is actually the branch of physics that deals with the study of charges at rest, meaning the charges are not moving, they are at rest. Okay, so this is an essential topic. Why? Because this is an introductory course in electricity courses. Okay, so once this charges starts to move along a conductor, that is not electrostatics anymore, but that is dynamic electricity, or that is in the process or in the study of circuits. Okay, so we are surrounded by electricity. Well, perhaps one of the most important discovery in our era was that when Benjamin Franklin actually discovered the electricity. Okay, so because trains, electronic gadgets, heating and cooling appliances, and many more electronic gadgets or those appliances that utilizes electricity would not simply work without the use of electricity. And even our brain uses electricity to work, though sometimes it just don't work. Okay, so what is an electricity? Electricity, to define it, it is an invisible force in nature consisting of two electrical charges, the proton and the electron. That is the basic idea of electricity. It is an invisible force, meaning we cannot see this electricity unless it sparks. There is a spark. Okay, so consisting of two electrical charges, basically the proton and the electron. So without electricity, again, our world today would not be the same without the discovery of electricity. Trains would not work. We could not discuss in our classroom because there is no projector which utilizes electricity. You cannot use your TV because without electricity. You cannot use your electronic gadgets, your iPhone or Android phone without electricity. So it is a very important discovery. So that's why there is a need for us to study the basics of electricity. Oh, so electric charge, the word electric is actually derived from the word electron, meaning amber. This amber is represented in our first picture here, which is actually a type of stone. They discovered that when this amber is rubbed with wool, in this second image, the amber could attract other objects. So, in other words, if this amber is rubbed with this wool, there are some processes that happens between the rubbing process of the amber and the wool, so that after the rubbing process, or what we call the charging by friction, okay, this amber could attract some other objects. So what happens? There is a process, or there must be something happening between this amber and this wool after they get rubbed with each other. Okay, and that has something to do with the electrical charges. Okay, so okay, electrical charge, plastic rods, and four are particularly good for demonstrating electrostatics. Well, in some of the experiments, uh, in the lecture of in the United States, they are actually demonstrating it for both lecture and laboratory in the classroom setting. So the interactions between electric charges at RS. Benjamin Franklin suggested to call the two kinds of charges, which are positive and negative charges. So the key concept is two positive charge or two negative charges repel each other. In other words, if we have the same charge, they tend to repel each other. Okay? So if we have a let's say if we have well, we have positive charge and we have a positive charge. These two try to repel each other. If we have unlike charges, positive and negative, these two charges attracts each other. So that is the key concept. Whenever we have two charges that are really the same, okay, have sign, the same sign, then they repel, and if they have opposite sign, unlike charges, they attract. Okay, so I'm sorry. Yeah, let's go back. So let's just recall some basic ideas, okay, about the proton and electron. We know that inside the what we call in an atom, we have the nucleus. This is the nucleus, okay, and inside the nucleus there are protons and what we call the chargeless neutron. So the proton is actually the positive particle inside the atom. Positive, that is the proton. And the negative charged particle inside an atom is what we call the negative, that is the electron. And, oops, that is the electron. Okay, let me just rewrite. That is proton. This is basic concept, electron. Okay, and of course, we have the chargeless particle we call the neutron. Okay, so the one that discovered proton is actually Sir Ernest Rutherford. Okay, Ernest Rutherford. And the one that discovered electron is actually Sir J.J. Thomson. J.J. Thomson. And the one that discovered neutron is actually Sir James Chadwick. James Chadwick. Okay. So going back in our model, inside the nucleus, we have the protons and the neutrons. And if we're going to continue our drawing with that, so for example, here is our nucleus again. Positive, positive. Okay, we have two neutrons, which are chargeless. And this nucleus is actually surrounded by what we call a cloud of electrons. So meaning to say, these electrons are free to move all around this nucleus. So the concept is the inside the nucleus is the proton and the neutron. And this nucleus is bounded by a strong force. These two particles are bounded by a strong force, what we call the nuclear force. So you would require a large amount of force for this proton and neutron to get out of the nucleus, and that is what we call the nuclear force. But we know that these electrons surrounding the nucleus can be easily be detached, okay, or transferred to any object or to any atom or element by simply applying a very small amount of energy, and that is what we call the ionization energy, the amount of energy required for this electron to jump from another atom or to another object. So hence, again, electrons is the one who is being transferred when we do the charging process. Not the proton and not the neutron. Why? Because again, they are bounded inside the nucleus. Okay? So that's why we have covalent bonding, ionic bonding. That is the transfer of electrons. Okay? That involves the sharing of electrons in terms of covalent, in terms of ionic, di ba? It gives off its electron. Okay? So that is the electron, not the proton and the neutron. Okay? So, electric charge and structure of matter. Well, again, the structure of atoms can be described in three particles. The electron, which is the negatively charged, proton, which is the positively charged particle, and neutron is the chargeless particle. The nucleus is composed of proton and the neutron, as I have said a while ago, and the atom is surrounded by the clouds of electron. And here are some facts. Here are some facts with regards to our atom. the mass of the positive charge or the proton is approximately equal to 1.673 times 10 raised to negative 27 kilograms, and the neutron has a mass of 1.675 times 10 raised to negative 27 kilogram. That is approximately equal to the mass of proton. So that's why in our study we can actually approximate that the mass of the proton is equal to the mass of the neutron. So the electron has a more, what do you call this? My mistake, the proton has a more massive mass compared to electron, because the mass of the electron is in terms of 9.109 or 9.11 times 10 raised to negative 31 kilograms. This is much lighter than the mass of both the proton and the neutron. Okay? And inside the nucleus, it composed 99.9% of the atom's mass. Why? Because there is the presence of the proton and the neutron. Okay? So, yeah. We have to take note of the following charges because this might appear, well, in your exam or in your quizzes or a trivia question. So, how did they measure that? Let's just trust the scientists, okay, that is the mass of our proton, neutron, and electron. Which is more massive? Again, the proton and the neutron compared to the electron. Okay? So, let's go back. So, net electric charge. When we are talking about the net electric charge, it simply means that we could have three cases. Okay? The net electric charge could be neutral. In other words, if an object or an atom or an element has a net neutral charge, meaning the number of electrons is equal to the number of protons, meaning the net electric charge is neutral. So again, let me just write it. So if we have a neutral object or a neutral element, the number of electrons is equal to the number of the protons. So we say that an object is a neutral if it has a number of electrons equal to the number of protons. And we say that we have a positive charge, net positive charge, okay, net positive charge, that indicates that the number of what? The electron is less than the number of protons. In other words, there is more proton than the electron. Okay? And the net negative charge, okay, net negative charge, it says that the number of electrons is greater than the number of protons. It's not easy or it's not hard to actually grasp the concept. Okay? So for example, we have a lithium atom. Okay? The atomic number of lithium, I'm not mistaken, is 3. As you can see here in the atomic model of the lithium atom, inside the nucleus, okay, represented by this, okay, there are 3 protons which are red and there are 4 neutrons. Okay? So, the case is, we call this a neutral lithium atom. Why? It has a net electric charge of being a neutral because the number of protons which are represented by the red spheres here is equal to the number of electrons which are represented by the blue spheres here. So we say that this atom is a neutral atom. So what will happen? What will happen if I'm going to strip off this electron by applying some certain amount of energy? Okay? What will happen is that In this second image, we have a positive lithium ion or a net positive charge of this atom. Why? Because again, I stripped off one electron from the original neutral lithium ion, and hence, what happened is that the number now of the protons is greater than the number of electrons. So we call this as a positive lithium ion or a positive charge, net positive charge atom. Because again, the number of protons is greater than the number of electrons. And again, what will happen if in this neutral lithium ion, I added another electron? Okay? So what happens is that we have now 4 electrons, 1, 2, 3, 4, but our proton still is 3. So it says that the number of electron is greater now in the number of, compared to the number of protons. So hence, what we call this is a negative lithium ion or a net negative charge atom. Okay, or element. So because the number of new electrons is greater than the number of protons. And we call that positive net charge, negative net charge, and zero net charge if electrons is equal to protons. Zero net charge, fewer electrons than protons, positive net charge, more electrons than proton, negative net charge. So as you can notice here, that the ones that are being transferred is not really the proton. That's what I've said a while ago, because the proton is bounded inside by a strong force, what we call the nuclear force, so that it cannot be easily, okay, transferred or get out of the nucleus. But the ones that are more easier to be transferred is the electrons rather than the protons and the neutrons. Okay? So, deficiency in electron, we call that positive net charge. Surplus of electrons in an atom or in an object, we call that a negative net charge. If the electrons is equal to the number of protons, we call that a zero net charge or a neutral charge. Okay? So, a neutral atom has equal number of protons and electrons. Okay? A positive ion has a deficit of electrons. Deficiency, meaning lacking of electrons. A negative ion has an excess of electrons or surplus of electrons. And again, ionization is the process of gaining or losing an electron. Electron, not proton. Okay? So, I hope you're learning. So, one important concept of charges is that charges is conserved. Charge is conserved. One important aspect of electricity that arises from experimental observation is that the electric charge is always conserved in an isolated system. So, for example, class, what we have seen a while ago, the Greeks observed that when amber is rubbed against the wool, after the process of rubbing, well, the amber could attract some objects. So, there is a charging that occurs, or there is an exchange of charges in the rubbing process to the reason why this amber could attract some objects. And again, one of the charging processes is what we call the charging by friction. Okay? So in this example, types of charging, we have to include that types of charging. Types of charging is one, charging by friction. Okay? In this example, class, for example, we have a glass rod, or what is that? A glass rod, and it is rubbed against the silk, which is the color red here. Okay? So what happens is that the electrons from the glass rod is transferred to the silk, okay, by the rubbing process. Because when we rub things together, we are actually creating heat. And heat is an energy. So you are giving the electrons in that glass rod, okay, the opportunity for its electrons to come out of its orbit and to be transferred to the silk. Okay? So, what will happen is that, for example, if this glass rod is neutral, okay, again, neutral, we say that an object is a neutral if its proton is equal to the number of electrons. So there is no net charge in this glass rod, for example, and we have a neutral silk. Okay, in this case, neutral again equal, the proton is equal to the number of electron. The number of proton is equal to the number of electron. So when these two objects are rubbed or charged by friction, okay, what happens is that the tendency is that the glass rod, because of the energy created by the friction in terms of heat, so what happened to the glass rod is that it gives off its electron to the silk. Okay? And the amount of charge lost by the glass rod is equal to the amount of charge that the silk has gained. So in this case, the glass rod transferred electrons to the silk, okay, and the silk gains an electrons from the glass rod. So the amount of electrons gained by the silk is the amount of the electrons lost by the glass rod. So what happened is that after the rubbing process, after the charging by friction process, what happens is that since the glass rod, okay, since the glass rod loses some electrons, what happens is that after rubbing, the glass rod became positively charged. Positively charged. Why? Because it loses now its electron. It gave its electron to the silk. Okay? So it loses some electrons. So there is an imbalance of number between the protons and the electrons in this glass rod. So we call that positive rod. Okay? We call that the rod is positively charged. And the silk, actually, what happened to the silk? Since it accepts electrons, okay, from being a neutral, it accepts new electrons. So what happens is that the silk became negatively charged. So after the charging process, the rod now becomes positively charged and the silk now becomes negatively charged. And again, the amount of charge, okay, lost by the rod, okay, the glass rod, this glass rod, is equal to the amount of charge gained by the silk. So there is no charge that is lost. Charge is conserved. That is the law of conservation of charge. Okay? So here are some experiments in electrostatics. So I'm just going to zoom it in. Okay? So for letter A for this figure, so if you have two plain plastic rods, okay, plain, meaning we have two neutral plastic rods. So if we brought this together, okay, close to each other, these two plain plastic rods neither attract nor repel each other. Why? Because these two plastic rods are not charged. Okay, and the requirement for us to have a repulsion or an attraction is that these two plain plastic rods must have what? A definite charge. Okay, in this case, if they have the same charge, they will repel. If they have unlike charges, they will attract. So suppose that these plastic rods are rubbed against the pore. So what happens is that we're going to charge these plastic rods by friction again. And by friction, what happens is that it turns out, class, that the plastic rod gain an electron from the pore. So what happens is that after rubbing, the plastic rods became negatively charged. Okay, both of the plastic rods. So after being rubbed with the pore, the rods now repel each other. Why? Because it is both negatively charged, so that this rod will actually go as much as far away, repel as much as far away from this negatively charged plastic rod. Okay? Because the key concept is like charges repel and unlike charges attract. So in our second case, class, second picture here, so what happens is that there is a glass rod, okay? And let's say that this two glass rod is again neutral, no charges, no net charge. So what happens if we brought this close together? If we brought this close together, what happens is that nothing happens because they are not charged, okay? So but once these glass rods are rubbed against the silk, it turns out that the glass rod gave its electron to the silk. So that's why the glass rod loses now an electron, and the silk gains an electron. So if the glass rod loses an electron, from being a neutral, it became a positive charge. Okay, because the number of positive charge is now greater than the number of the negative charge. So what happens that they were both rubbed to the silk, and if we're going to brought these two glass rod again together, since they have the same charge, they will still try to repel each other. Okay? So, but in our letter C, image letter C class, the interaction between objects with opposite charges. So what happens is that if the plastic rod and the glass rod, if we brought these two together, since the glass rod after rubbing process, after the charging process became positively charged and the plastic rod became negatively charged, if we brought these two together, certainly they should attract each other because they have opposite charges. Okay? And what happens, and the pore in the silk each attracts the rod it rubbed. So for here, negatively charged plastic rod, it should be attracted to the positively charged pore. And of course, the glass rod should be attracted to the negatively charged silk. Okay? So I hope you're getting what I'm trying to say. These are experiments in electrostatics. So, what are the types of material in terms of their conductivity? So, we have what we call the conductors, the insulators, and the semiconductors. So, the conductors are basically from the word itself, okay, is a material that permit or conduct electric charge to move easily from one region of the material to another. Good conductors are basically metals, okay, and one of the best conductor that that has its best conductivity is the what? Do you think it's copper? Best conductor? If you think copper is the best conductor, then that is a no. But copper is the most commonly used conductor. Okay? That is the most commonly used conductor. But the best conductor is what we call the silver. Okay? So this is the best conductor. So sir, why are we not using silver for all of our wirings or even gold? Okay, you are in the Philippines. Okay, you are in the Philippines. Well, of course, we are in the Philippines. We ought not to use silver because it might get rubbed. Okay, so the most commonly used conductor is the copper. Okay, that's just a trivia. Okay, and let's go back to conductors. So conductors, in other words, these are the material that permits electric charge to move easily from one region of material to another. And we have what we call the insulators. The insulators is the materials that do not easily permit the electric charge to flow. So insulators, in other words, is the opposite of conductor, wherein insulators do not permit the electric charge flow, easily permit. So what are the examples of insulators? Well, we have the rubber, we have the plastic, we have the wood. So these materials are good insulators. Okay, we have the air, that's a good insulator. Okay, so and of course we have what we call the semiconductor. It is a material that has an intermediate property of conductor and insulator. So semiconductors are actually 50% conductors and 50% insulators, or semiconductors, we can say that sometimes this semiconductor can conduct and sometimes it cannot, or sometimes this semiconductor can control the amount of charge flowing in its material, in its body. So semiconductors are actually used in our electronic gadgets or in our electronic gadgets, because it limits the amount of charge that should be flowing on our laptops, on our cell phones. Okay, so semiconductors, that is sometimes it can conduct and sometimes it cannot, or sometimes it can control the amount of charge flowing on that material. Okay, so that are the materials in terms of its conductivity, classification of materials in terms of its conductivity to conduct charge. Okay, for our image here, we have The first one, we have discussed the types of charging, the charging by friction. But now we're going to discuss the second type of charging, that is the charging by conduction. Okay, so charging by conduction. So what does this mean? So for example, we have here an insulating stand and the insulating nylon threads, and we have a metal ball. And metal ball, when we say a metal, that is a good conductor. Okay, and we have here a charged plastic rod. Okay, that is a negatively charged plastic rod. Okay, what will happen, class, is we're going to charge the metal ball by placing a copper wire as a connection from the metal ball to the plastic rod. So what happens is that since this is a negatively charged plastic rod, if we're going to put one end of the copper wire to this plastic rod and the one end of the copper wire to the metal ball, what happens is that since this is a conductor, copper is a conductor, of course, copper is a conductor. So if it is a conductor, it allows the flow of charge easily from one region to another. So if we're going to connect these two by this copper wire, so the negatively charged particle of this plastic rod flows through this copper wire. This metal ball before charging is neutral. Positive charges is equal to the negative charges. Proton is equal to the number of electrons. So, but once this is connected via copper wire, okay, to the negatively charged plastic rod, some of the negative charges of this plastic rod flows through the wire and reaches the metal ball. So that if we're going to remove now the copper wire, the tendency is that this negatively charged plastic rod still is negative. And what happened is that since the metal ball gains another electron or negative electric charge, what happens is that after the charging process of conduction, so the metal ball now becomes negatively charged. And when this negatively charged plastic rod is brought close near to the metal ball, it would simply repel. Okay? So the same likewise if we have a positively charged glass rod, if we have a positive charged glass rod, so if we brought this near to the metal ball, what happens is that it would attract the metal ball. Because again, positive like charges repel and unlike charges attract. So this is now charging by conduction. There is a physical contact in between the charged plastic rod and the metal ball via the copper wire. Okay, that is charging by conduction. So charging by induction. Okay, induction. So this is charging. Let's go now to charging by induction. Charging by induction. So charging by induction, this is the charging process that does not involve contact. Okay, does not involve contact. So for example, we have here a metal ball. Okay, let's say we have a metal ball. This metal ball is again neutral, meaning the number of protons equal to the number of electrons. And it is actually standing on an insulating stand so that no charges could flow here because this is an insulator. Okay? So, what happens is that we have a negatively charged rod here and this is brought close but not touching the metal ball. Okay? So, what happens is that upon bringing this negatively charged rod close to the metal ball, there is a separation between the positive charges and the negative charges in the metal ball. As you can see here, that the number of positive charges, that the number of positive charges here in our figure, we have 4 positive charges and we also have 4 negative charges. So this indicates that this metal ball is neutral. But because of the placed negatively charged near to the metal ball, some of the positive charges are suspended to the left side of the metal ball because it is being attracted by this negatively charged rod. And some of the electrons are left being in the right side, will go to the right side of the metal ball there is an atomic separation between the positive charges and the negative electric charges, because these negative charges want to go as much as far away from this negatively charged rod. Okay? So, what will happen, class? So, what will happen if I'm going to put a wire on the metal ball, and this wire is connected to the metal ball and the other end of the wire is connected to the ground, or in other words, to the earth. It turns out that the earth is a large conductor. It has numerous charge, okay, negative charge and positive charge. So what happens is that uh, since this negative charge would want to go as much as far away this negatively charged, if I put a wire, that a wire is a good conductor, so what will happen? The negative charges here will actually escape through the metal ball, through going to the wire and reaching the ground or the earth. So the electrons will run, okay, from the metal ball to the ground through the wire. So because it wants to go as much as far away this negatively charged, so what will happen is that the negative charge now is in the ground after we remove the wire. So what happens is that we are left with positive charges here, and still we have the negatively charged particle rod here. So that if we're going to remove now the negatively charged rod here, so it turns out that this metal ball now will be left only by the positive charges. Okay, so what happens is that we now have a positively charged metal ball. Okay, so the electrons rearrange themselves. Ball has overall electron deficiency, net positive charge. Okay, so do you understand that? So that's the concept of induction. So the concept here is that it does not involve contact. So the two objects that are charged or that we want to charge each other are not involved in contact. Does not involve contact. So the negatively charged rod is not to have a contact here in metal ball, and we have done that by charging by induction. Okay, so yeah. So I have a question. So what will happen if we replace this negatively charged rod by a positively charged rod? Okay, so let me just give you a second to think. If we replace this negatively charged rod with a positively charged rod, so what will happen? Okay, so let's try. So for example, I have here the metal ball, this metal ball, okay, okay, and this is now my positively charged rod, okay. I brought it close to the metal ball, and again, well, of course, if I brought this close positively charged glass rod to the metal ball, some of the negative charges will be suspended to the left of the metal ball because it is attracted to the positive charge glass rod, and some of the positive charges will actually try to repel or go as much as far away to this glass rod because they are repelling each other. So what will happen, class, is if I'm going to connect a wire and then connect it to our ground or to the earth. Okay, this is the wire. Okay, so what will happen, class? What will happen? So, it is very impossible that the positive charges will run through the wire. Again, what I'm saying is that these positive charges cannot move. Okay? But the electrons is the one that can only move. Okay? So what will happen? So it turns out that the ground is a huge conductor. It has a large amount of negative charges in it and positive charges. So what will happen is that some of the electrons from the ground will actually come up through the wire, okay, and try to neutralize these positive charges. So what do I mean by neutralize? Is that it would replace these positive charges, okay, it would replace these positive charges so that this would be neutralized by the negative charges or the electrons. So that if we're going to remove the wire, let us remove the wire. Okay, if we're going to remove the wire, So what happens is that you are left with negative charges. And then if you're going to remove this, so the electrical charges or the negative charges arrange themselves again, okay, in the center. So this will now be our metal ball. So what happens is that we have charged the metal ball as negatively charged metal ball. Negatively charged metal ball. Okay, so it's possible. Okay. So that is charging processes. So electric forces on uncharged object. So after you electrify a comb by running it through your hair, sometimes you can pick up uncharged bits of paper with the comb. Have you experienced that? So it's a very dry condition. It's very hot condition, and you try to comb your hair, and after sometimes you accidentally put the comb on a small pieces of paper, and then you notice that this comb could actually attract some that small pieces of paper. Okay? So this interaction is what we call the induced charge effect. Okay? So what happens here is that the charges within the molecules of an insulating material can shift slightly. So as you can see, paper and the comb are insulators. So the charges within the molecules of that insulating material can shift slightly, and that is what we call the polarization. That is the atomic level of separation of charges in insulator. So what do we have here is that if we're going to analyze it here, class, so what happens is that after we comb our hair, because that is basically charging by friction, okay, you are creating heat while you are actually combing your hair, diba? Because there is a charging of friction between your hair and the comb. And if the comb becomes negatively charged, okay, so what happens is that if you put it placed to another insulator, which is a paper, so the paper's atoms could shift slightly. Okay? So, if this is a negatively charged comb, so what happens, there is an atomic level of separation, as you can see here, atomic level of separation between the positive charge and the negative charge, so that the positive charges are aligned in this side because it is attracted to the negative charge, and the negative charge is what? Try to repulse or to move away from this negative charge. So that if we're going to accidentally put these two insulators together, it would attract some paper. Why? But with a very, 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 very weak force. Okay? So that it appears here in our image. Okay? So there is an attraction between. So, for example, for a positive, so if you comb your hair and it became positively charged comb, so reverse thing will happen. This time, the electrons in the molecule shift toward the comb. So electrons, 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 and so that the negative charges in each molecule are closer to the comb, okay? And feel a stronger force from it than the positive charges because it tries to repel. Again, the net force is attractive. Okay? So it's worth taking these examples. Okay? So anyway, electric charge again, when a material has an excess number of electrons, it has a negative electrical charge, okay? Net negative charge. But when a material has a deficiency of electrons, meaning lacking of electrons, it has a positive charge. And again, like charges in our image here, repel each other. Okay? Positive, positive, repel, negative, negative, repel, and opposite charges attract each other. Hi, so we will continue our discussion all about electric charge that in terms of numbers. So electric charge can be represented by the symbol Q. My mistake because this should be lowercase q or small letter q because uppercase Q in terms of thermal physics is actually the heat, okay? With the unit code Coulomb, okay? Named after Charles Augustin de Coulomb, that is represented basically by a big C. So the unit of electrical charge is named after Charles Augustin de Coulomb. So usually in terms of our study here in physics, okay? So the charges is ranging from 1 microcoulomb, okay, of charge, or 1 nanocoulomb, or even 1 picocoulomb. So this is equal to 1 microcoulomb is 1 times 10 raised to negative 6 coulomb. 1 nanocoulomb is 1 times 10 raised to negative 9 coulomb. And 1 picocoulomb is 1 times 10 raised to negative 12 coulomb. So this, in our study, we will be, in our computation, will be frequently seeing these ranges of charges, okay, the values of charges in terms of micro, in terms of nano, in terms of pico, okay. So again, coulomb is the unit of charge denoted by big letter C. Okay, so Coulomb found out that each electric point charges exerts a mechanical force in each other, on the other. So in other words, Coulomb found out that whenever we have two single point charge, okay, point charge, this 2 point charge exert force on each other, mechanical force on each other. So that if we're going to write it in our formula class later on, we will see that there is a great relationship of in terms of the distance between these two charges to the electric force experienced by the two charges. So 1 coulomb of charge is basically equal to 6.25 times 10 raised to 18 electrons. That's a numerous amount of electrons. Okay, so this is trivia. Okay, 1 coulomb is equal to 6.25 times 10 raised to 18 electrons. So Coulomb's law states that the magnitude of the electric force between the 2 point charges is directly proportional to the product of the charges Q1 and Q2, the product of the charges, and inversely proportional to the square of the distance between them. Here we can see that F is equals to 1 over 4 pi epsilon sub 0, where epsilon sub 0 is what we call the permittivity of free space, and it has a value of 8.854 times 10 raised to negative 12 farads per meter. Don't worry about the farads per meter. We will discuss it on the capacitors or a capacitance. So Q1 and Q2 are the charges in Coulomb. R is the distance between the charges. Okay? So what are we going to do here is that according to Coulomb, the magnitude of force of the electric force between 2 point charges is directly proportional to the product of the two charges and inversely proportional to the square of distance between them. So let me just rewrite this equation. Okay, so force according to Coulomb is 1 over 4 pi epsilon sub 0, okay, times Q1, Q2, this is the product of the charges, multiplied by this, divided by the square of distance between them. Actually, this 1 over 4 pi, 1 over 4 pi epsilon sub 0 could be actually replaced by what we call the Coulomb's constant K. Coulomb's constant K. And basically, this Coulomb's constant is approximately equal to 9 times 10 raised to 9. Its unit is Newton meter squared per Coulomb squared. Why does that happen? Because 1 over 4 pi epsilon or epsilon sub 0 is the permittivity of free space, that is 8.854. Shift constant 32 of your Casio calculator, negative raised to negative 8.854 times 10 raised to negative 12 farads per meter. If you're going to evaluate that on your calculator, let me just recheck. Okay, 1 over 4 pi 4 pi shift constant 32. Okay, that is equivalent to 8.98 times 10 raised to 9, or approximately equal to 9 times 10 raised to 9 Newton meter squared per Coulomb squared. So our formula from this, okay, from this will be changed to this. So this equation is simply equal to what we call the Coulomb's constant K, now equal to K Q1 Q2 over R squared. So this will now be our formula for the force, okay, between two charges. So, okay. So let's try to have a sample problem. I have here a sample problem. Okay. So the electron and proton of a hydrogen atom are separated by a distance of approximately 5.3 times 10 raised to negative 11 meters. Find the magnitude of the electric force between the two particles. Okay. So the given here is the distance between the electron and the proton. We have the R. That is basically 5.3 times 10 raised to negative 11 meters. Okay? So it's important that the distance is in terms of meters because Coulomb's constant is in terms of Newton meters squared per Coulomb squared. Okay? So if the given distance is not in meters, you have to convert it into meters. Okay, so what is the charge here? So for example, if we're going to draw the problem, we have here the electron and the proton of a hydrogen atom. So for example, this is the nucleus of the hydrogen. This is the proton, okay, inside the hydrogen, nucleus of the hydrogen, and surrounding it is the electron. So the distance between the electron and the proton is what we call the R. Okay? So, find the magnitude of electrons between the two particles. So, what will happen here is that the charge of proton and the charge of electron is actually constant. The charge for proton is 1.6 times 10 raised to negative 19, and again, the unit of charge is Coulomb. Charge of electron is negative 1.6 times 10 raised to negative 19 Coulomb. Okay? That is constant. The charge of proton and the charge of electron is the same, but their sign is not the same. Okay? But in our problem, find the magnitudes of the electric force between the two particles. So we are asked to find the magnitude of the electrons. So if it is magnitude, it implies that the magnitude of the force should be positive because magnitude, we are asked for the magnitude. So what are we going to do here is that F is equals to K, Coulomb's constant, times Q1, which is our Q proton, charge of proton, times Q sub E, which is our charge of electron, divided by the square of distance between them. So, K now is 9 times 10 raised to 9 Newton meters squared per Coulomb squared, times the charge of proton, 1.6 times 10 raised to negative 19 Coulomb, multiplied by the charge of the electron. And take note, we have to use a positive charge here because we are asked for the magnitude. So we have here 1.6 times 10 raised to negative 19 Coulomb divided by the square of the distance between them, which is 5.3 times 10 raised to negative 11 meters. Okay? So what must be the magnitude of force that these two particles or these two charges experience? By the way, the force is attraction. Okay, because electron and proton have the same or different charge, different charge. So the tendency is that the force they are experiencing is attraction. So the answer should be 8.2. The unit of force is Newton. 8.2 times 10 raised to negative 8 newtons. Okay? So that should be our answer. Okay, for number 2 problem, 2-point charges Q sub 1, 25 nanocoulomb and Q sub 2, negative 75 nanocoulomb are separated by a distance of 3 centimeters. So we have here Q sub 1 is positive, a positive charge. Why? Because 25 nanocoulomb, its charge is 25 nanocoulomb, positive 25 nanocoulomb. So this would be Q sub 1, and charge 2 is a negatively charged particle. Why? Because it has negative 75 nanocoulomb. So charges or the sign of the charges is important. Okay? And these two are separated basically by, again, the problem says 3 centimeters. Okay? So, find the magnitude and direction of the electric force that Q1 exerts on Q2. Okay, this is Q2, Q sub 2, charge 2. So, letter A, find the electric force that Q1 exerts on Q2. That Q1 exerts on Q2. That means that Q2 experiences a force that is what? With respect to Q1 in this direction. Because this charge is attracted to this. Okay? And letter B, the electric force that Q2 exerts on Q1. So, this Q1 also experiences an attraction in this direction because of Q2. And these two, okay, let's call that the force of 1 to 2. Okay, force of charge 1 to 2. Okay, and this is for F1, 2. Force of charge 1 to 2. And this is F2, 1. Force of charge 2 on 1. So, and these two charges or these two forces are equal. Okay? Law of interaction. Okay? So, F21 is equal to F12, and that is basically K again, Q1 times Q2 over R squared. But our R is in terms of 3 centimeters, so we have to convert it into meters, 0.03 meters. Okay? So, we have now to compute 9 times 10 raised to 9 Newton meter squared per Coulomb squared. That's the unit of the Coulomb's constant, multiplied by Q sub 1. Okay, our Q sub 1 is given by here 25 nanocoulomb. Be careful, 25 nanocoulomb is 25 times 10 raised to negative 9 coulomb. Okay, multiplied by what? Again, magnitude. Okay, magnitude. So if the problem is asking for magnitude, we should use positive. Okay, even though it's negative. 75 nanocoulomb. Okay, that is the same 75 times 10 raised to negative 9 coulomb. You must input into your calculator the times 10 raised to negative 9 coulomb. Okay? Divided by 0.03 meters squared. Okay? So the forces F12 is equals to F21 is now should be now equal to 0.019 newtons. So 0.019 newtons. And its direction is actually what? The direction is actually attractive. Okay, because we do have the same, or we do have different charges, because unlike charges, they will attract. Okay? So, 2-point charges for number 3, we have 2-point charges on the positive x-axis of the coordinate system. So, charge Q sub 1, 1 nanocoulomb is 2 cm from the origin, and charge 2 is negative 3 nanocoulomb is 4 cm from the origin. What is the total force exerted on a charge Q sub 3, 5 nanocoulombs located at the origin? Gravitational force are negligible. So, in this problem, it is involved in a coordinate system. So, basically, charges, we are analyzing charges with respect to the coordinate xy. So, what are we going to do is, first, 2-point charges located on the positive x-axis. So, we have to draw a x and y coordinate here. Okay? Please forgive me for my drawing. It's not even straight. Okay? Y and x. So, charge Q sub 1 is located, okay, according to the problem, is located 2 cm from the origin. So, this is our origin. Okay, this is our origin. 2 cm away, so we can put this charge here. This is Q sub 1, okay, which is a positive charge, of course. And we can put Q sub 2, according to the problem, is 4 cm away from the origin. So 4 cm in the positive x-axis, 4 cm, this is Q2, which is a negative charge. So the distance of this with respect to the origin is 2 cm, okay? And the distance of this with respect to the origin, okay, origin itself, here, the origin is 4 cm. And what is the total force exerted on a charge Q sub 3, 5 nanocoulomb located at the origin? So we have a charge at the origin, which is a Q sub 3, which is a positive charge. The problem is actually asking what is the total force exerted by these two charge Q sub 1, Q sub 2 on the third charge located at the origin. Okay? What is the total net force exerted by these two charges on the third charge? So what are we going to do? Our point of interest here is the charge 3, because that is the problem. That's what the problem asks. So what are we going to do is, if we're going to analyze Q sub 3 at the origin, so this is Q sub 3. We have to draw the free body diagram of that. Q sub 3 is a positive charge. So there are two forces acting on this charge. One is the force due to Q sub 1. Agree? Okay? Q sub 1. Okay? and 1 is the force due to Q sub 2. So we have to analyze the free body diagram, the directions of the force of these charges exerted on charge 3. So this is the free body diagram, FBD. Okay? So, this charge 3 will experience a force in this direction. Okay? Why? This is a force of charge 1 due on 3. Okay? In this direction to the left. Why? Because this is positive charge, Q sub 3, and Q1 is also positive charge. Therefore, this charge 1 will try to push this Q3 as much as far away from itself. Okay, so hence this is the force of charge 1 on 3. Hence F13. And of course, we have to analyze also that there is a second charge here, Q sub 2, which is a negative charge. So negative then positive. So we would be having a force in this direction due to the negative charge Q sub 2. And we will call it F, the force of 2 on charge 3. Okay? Why in this direction? Why to the right? Because this negative charge attracts the third charge on the origin. Okay? So, now, if we're going to get the summation of forces along X, okay, that would be the total net force. And that should be going to the right is positive F23 minus F13. Okay? So, that is the uh, equation to get the total net force on charge 3. Okay. So, if you're going to assign already the signs, so F2, in computing F23 and F13, we should be using the charge Q in Coulomb's law as positive. Okay? So, to get F23, we have what? KQ2 Q3 over R squared minus KQ1 Q3 over R squared. Okay, and the distance of charge in this R, the distance of charge 2 to charge 3 is this R. And this R is the distance between charge 1 and charge 3. So we have to have 9 times 10 raised to 9. Okay, so Q sub 2 is equal to, okay, again, as I have said a while ago, if you perform this already, if you assign the direction already of the forces, well, you have to use the positive charge whether this, even if this charge 2 is negative. So you have to use 3 nanocoulomb multiplied by that charge 3, which is 5 nanocoulomb, and divided by the R. What is this R? The distance of charge 2 to charge 3, and that is given by 4 cm. Converting it into meters, that is 0.04 meters squared minus 9 times 10 raised to 9. Q1 is 1 nanocoulomb and Q3 is 5 nanocoulomb. Okay, 5 nanocoulomb multiplied by the distance, the square of, divided by the square of the distance between Q1 and Q3. Q1 is to Q3 is 2 cm away, so that should be 0.02 meters squared. So upon computing that, we shall have a net force. We shall have a net force of equal to 28 micronewton. 28 micronewton going left. Okay? So if you compute that, your answer, if you compute this, your answer would be negative 28 micronewton. The negative indicates that the direction of the net electric force experienced by charge 3 is going to the left. So hence, we concluded that the F net is 28 micronewton, and that negative, we said that is going to the left. Okay? So I hope you understand the basic concepts in electrostatics, Coulomb's law, and for the upcoming videos, and I'll be posting more problem solving involving Coulomb's law and multiple choice questions, probably in electrostatics and charges. So thank you so much for listening, and I hope you enjoy this watching this video. If you find this video helpful, please don't forget it to share to your friends and to your classmates, and so that it can be also a help for them. So thank you so much for listening. This is Engineer Abat. Thank you for listening, and God bless you.